What's up, people of calculus? We're going to talk about another series convergence test today. It's called the integral test. And then an offshoot of that will be a P-series test. So what do you need? You need, again, a healthy respect for infinity. It's tough for us mere mortals. You need to know improper integrals. All right, so improper integrals, DOE with the integral test. We're going to be using some improper integrals. So again, refresh your memory if you need to. You can backtrack and look at some of those, watch one of those videos. And you need to know about a number line, like what number is in relation to another number. Sounds pretty obvious, right? So let's go. Let's do some Riemann sums. A Riemann sum was something we could use to approximate the value of a definite integral. So let's kind of look at some of those. For the function 1 over x squared. So the function 1 over x squared is positive, it's decreasing, and it converges to 0 at infinity. So all things that are important in the realms of series. We want to tie the series 1 over n squared to the function 1 over x squared. You can see how there's like a tight relationship there. So let's take a look at what that is. All right, so here is the function, right? So there's the function 1 over x squared. Got a little bit of a hiccup there. So the improper integral from 1 to infinity of 1 over x squared with respect to x is 1. Now, you don't believe me, you can go ahead and do the integration yourself. But take my word for it, it's true. So we're going to do a right Riemann sum. So a right Riemann sum with subintervals of 1, you get a picture that looks like this. I didn't get all of the Riemann sums in there, but you can catch the drift as this continues on and on and on into infinity. So the areas of all of those rectangles, right? The green rectangle on the subinterval from 1 to 2 is going to have a height of f of 2. The purple rectangle down there is going to have a height of f of 3, and then a height of f of 4, et cetera, et cetera, et cetera. So you end up with a sum. Okay, so the Riemann sum, see the connection? The Riemann sum for this 1 over x squared would end up looking exactly like the series that we want to determine converges or diverges. Okay, so we can tie together the idea of a Riemann sum, an old idea, to a new idea, infinite series, because again, all new math is just old math repackaged. Okay, so this infinite series we saw, I think in the previous lesson, right? We were trying to determine, I was talking about a series as a sequence of partial sums. And we actually looked at that series and trying to figure out its partial sum sequence, and we never figured that out. Well, we're going to talk today about how to show this thing converges or diverges. So we can make the connection between the Riemann sum, right? Again, it was a right Riemann sum, and right Riemann sums under-approximate decreasing curves. So we can conclude that the Riemann sum is less than the convergent improper integral. Therefore, this infinite sum from 2 to infinity of 1 over n squared is less than 1. That means we're less than a finite value. That means we have to converge as a series. Now, on the flip side of things, if we think about a function, just a generic function f of x that's also positive and decreasing, let's just pretend that we did the integral from 1 to infinity of this function, and we showed that it diverges, right? It went off to infinity. Well, if we do a left Riemann sum for that generic f of x, right, that would look something like this, right? We've got this decreasing, going to 0 function. Now we got a left Riemann sum. Now that green rectangle down there would have a height of f of 1. The purple rectangle is going to have a height of f of 2. The black one's going to have a height of f of 3, then f of 4, et cetera, et cetera, et cetera. And you know that a left Riemann sum over approximates the actual area, And by the way, the improper integral diverged. So if this infinite sum, f of 1, f of 2, f of 3, etc., so the sum from 1 to infinity of this function of n, aka a series or a sequence, we can show that that diverges, right? Because it's bigger than an infinite area. So it has to be also divergent, also infinite in size. So this is the heart of the integral test. And maybe some of you are thinking that the beginning a few terms, like, well, one of those you started at 2 and one of those you started at 1. It really doesn't matter about the first few terms, like the first 1 term or the first 6 terms or the first 100 terms. It's not about that finite chunk at the beginning. It's about the infinite stuff at the end. So don't get too caught up with that. Just understand here that Riemann sums over and under approximate decreasing curves, and thus we can get to this idea of the integral test. So the integral test says this. If the sequence a sub n is positive and decreasing, and a sub n can be mapped to f of x, so the function itself that is continuous at all x, right, matches to the sequence, which is a discrete thing and it only exists at the integers, right? But if they line up, then both the improper integral from 1 to infinity of f of x dx and the infinite sum from 1 to infinity of the sequence a sub n, they'll do the same thing. They're either both going to converge or they're both going to diverge. Now, a little bit about that is that this test is only a test for convergence, okay, or divergence, right? It doesn't say that the value of the improper integral is the value of the infinite sum, right? That's not tying those two things together. What the integral test is doing is it's tying together that it's either infinite or it's finite, right? So if you get that the infinite improper integral is like 6, that doesn't mean that the series sums to exactly 6. It just means that the series converges to a number. So be careful that you don't tie together the value. Don't be so concerned with the value. It's more important that the improper integral converges or diverges. Don't feel compelled that you have to. If you can nail down that the improper integral converges, you know that the series also converges. And if you know the improper integral diverges, you also know the series diverges. Okay. So that's a bogus thinking. Be careful of that. So let's look at this example here. Use the integral test to determine the convergence for the series from 2 to infinity of log n over n. Now, the integral test is going to come in handy when you can integrate the function, like log x over x. Don't feel compelled to integrate everything, right? If you're kind of like shaky with your integration techniques and you don't feel so confident with the being able to integrate and like, don't sweat it. There's going to be some that are obviously easily integratable, but there's going to be a few more tests too. So if this isn't your cup of tea, then okay, work at it, right? You still need to be able to know how to integrate. But there's other tests available to us. Integral test is not the be all end all. So again, back to the series at hand. Okay, f of x is equal to log x over x is a positive decreasing and easy to integrate. So the integral test is going to be a good choice. So follow me through here. The integral from 2 to infinity of log x over x dx. All right, we'll go through the limit process. All right, so we want to say that's the same as the limit as b goes to infinity. The integral from 2 to b of log x over x dx. Hit it with the u filter. U is log x. Du is 1 over x dx. And you can actually find the integral of log x over x to be log of x quantity squared over 2. So then we'll sub that back in. All right, so the limit as b goes to infinity of the log of x quantity squared over 2. So check this out. What happens to the log of b as b drives off to infinity? Well, it gets infinitely big. And if that's the case, then this infinite integral diverges. It's infinite in size. So what does that tell us about the original series? Well, it tells us that the original series is also infinite in size because it can be tied to that improper integral. That's how we're going to use the integral test. Let me show you another one. So the harmonic series, ooh, not that kind of harmony, but, well, I don't even know what that was, honestly. What was that? The harmonic series is a very important series. It's in a very important series. It actually does tie to music. Pythagoras did a lot of work with like octaves. And listen, I'm not a musician. You might have seen the guitar behind me in class, but I don't profess to be a musician. But there's some great YouTube videos out there about the harmonic series as it pertains to music. And it blends together this idea of music theory and mathematical theory that is just, oh, it's awesome. I strongly encourage you to go look for those. I might even give you a link to one if you can't find it on your own. But the harmonic series is very important. It's going to come up over and over and over again. That is the series that is like 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, et cetera, et cetera, et cetera. Just 1 over n from 1 to infinity. Now we can tie that to the function 1 over x. As we integrate 1 over x from 1 to infinity, we can see that that is going to eventually be infinite. It's going to diverge, right? Because log of b trends off to infinity. So that says that the integral is the area under the curve from 1 to infinity of 1 over x is infinite. Therefore, the infinite series, the harmonic series, is divergent. Okay, that one's weird because of the false nth term test, what we get in trouble with, right? 1 over n is getting smaller and smaller and smaller. So we want so bad to say that it converges, but we can't say that with any assurance, just if we base that decision off of the sequence trending to 0. That's another reason why the harmonic series diverges. All right, let's look at another one here. Determine the convergence of, all right, the sum from 1 to infinity of 2 over n raised to the pi. This is a weird one. I thought I'd come up with a weird one here. Now, 2 over n to the pi can be connected to the function 2 over x to the pi. So if we integrate 2 over x to the pi, we'll just use a little power rule, right? That's 2x to the negative pi. So we'll add 1 to that and divide by that new power. So the limit as b goes to infinity is going to work out to be, look at all that beauty. Look at all that beauty down there. It's going to work out to actually be 2 over pi minus 1. So what does that tell us? That tells us that the improper integral, the infinite area from 1 to infinity under the function 2 over x to the pi, is a finite value. It converges to this 2 over pi minus 1 value. What does that mean about the series? Well, by the integral test, it means that the series converges. Not necessarily to 2 over pi minus 1, and probably not, but just that the integral converges. All right? So this leads me to an old problem that I gave you. You got this for your improper integral homework. Now, it was to figure out what values of p make the improper integral from 1 to infinity of 1 over x to the p converge. And you might have thought, like, well, this is just kind of an easy way to see whether an improper integral converges or diverges. But what it does is it now gives us a whole new family of series, because that integral, 1 over x to the p, from 1 to infinity, converged only when p was greater than 1. So listen, every series that looks like 1 over n to the p is going to be called a p series. And it will converge for p greater than 1. These are wicked Boom, easy. Anything that looks like 1 over n to the p will converge if p is greater than 1. These are wicked easy. Check it out. We got 3 series here. We're going to determine immediately whether they converge or diverge. So look at the first one, 1 over root n from 1 to infinity. Well, what is the power of n? That is a p series. It's 1 over n to the 1/2. 1/2 is less than 1. So it's going to diverge. What about the next one? Hello? Can y'all see this kid? Look at this kid playing FIFA while I'm trying to work. Unbelievable. All right, back to the math. 1 over the cube root of n to the 7th. Well, that is a p series. P is 7/3. That's right. Well, 7/3 is bigger than 1. That means that series converges. It's a p series. It's a snap. This last one here, 1 over 2 to the e, 1 over 3 to the e, 1 over 4 to the e. Doesn't that line up with 1 over n to the e? And guess what? E is bigger than 1. That means it's a convergent p-series. P-series are a snap. Very easy. All right, so if you can tie a function to a sequence and tie the infinite integral to the infinite series, if that infinite integral converges, so does the series. If the infinite integral diverges, so does the series. And there are some series that are in a certain format, and that is 1 over n raised to the p. Those are called p series. P series always converge if p is greater than 1, and they diverge if not. And by the way, the harmonic series, wasn't it a p series? Because it was 1 over n to the 1, and it diverged. Well, p wasn't bigger than 1, so of course we knew that it was going to diverge. Hey, ain't that special? All right, next time we're going to talk about a comparison test. Take what we learned here about p-series, and we're going to go to the next lesson and talk about how to compare weird-looking series to simple series like geometric series and p-series. So look for that one. Can't wait to show you. All right, peace.